Deep.
Are we on?
We are on. So we're continuing on with reliability.
We are. So we are here with Mansoor today. So for those of you that didn't see the video with AP last week, we highly recommend you go check it out. And then today we're going to spend some time with Mansoor. Yeah. So could you introduce yourself a little bit?
Hi, I am Mansoor. I've been with the Service Fabric for almost 10 years. So
That's it? That's it?
I started when it was not really called Service Fabric. So we had some prototypes. Okay, it was some earlier implementation of the concepts. And then we finally started the Service Fabric and like the same protocols, implementation, etc. And since then I've been with the team. And I've been mostly working almost, I think, except the first few months, I've been working in the Failover Manager area. And it's a central component and controls a lot of what goes on in the cluster.
Cool. So that's what we're going to learn a little bit more about today.
Okay.
So we call it the FM when we refer to it.
Yeah.
There's also this other thing that we call the FMM.
FMM.
Yeah.
Right.
What is that?
So that's the failover manager, right? So something that manages the failover manager.
Okay.
Right.
So
we can spend some time on that, but I think the core is the failover manager, right? And if you look at the code, the failover manager, FM and the FMM, like 99% of the code is exactly the same. They share the same code. Okay, so there are few places where we have this if else thing. If FM do this, else do this, but like 99% of the code is the same. Okay, so like once we cover one, okay, we automatically cover the other one.
Sweet. So let's talk about the FM.
So FM is the failover manager, as we know, but it does more than just the failover management aspects. Okay, so it closely collaborates with the load balancer, placement and load balancer. We call it PLB, and the reconfiguration agent. So the job of failover manager to have a global view of the system, meaning what are all the nodes in the cluster and what are all the services that are running, applications, partitions, replicas. It has a global view of everything. Okay, and then it also facilitates in creation and deletion of new services. Okay, so when a create request comes in, okay, it's the request from the user, it terminates at the FM.
I see.
Okay, and once everything is at steady state, everything is running, then it reacts to failures. If a failure happens, then it detects that the failure has happened and takes appropriate action to bring everything back to a healthy and functional state. Okay. And this is where it collaborates with the reconfiguration agent and the load balancer, etc. Another thing that the FM does is upgrades. Okay, so it also participates in the upgrade. In fact, it's the one that's orchestrating the upgrade. Okay, like UD by UD. And what we want to make sure during upgrade is that we have zero downtime. Okay, so despite failures happening, replicas moving around, multiple nodes being in the same upgrade domain, etc., the service keeps up and running all the time. Okay, so this is what it ensures. It works for the application upgrade and also the upgrade of the Service Fabric itself. Okay, so it does both. Okay, and then the third thing it participates is in the repair management and MR, the Azure upgrade, the OS patching, etc. Right, because they require pretty much the same semantics, right? So before we start patching a node, right, or upgrading the software operating system on a node, we want to make sure that okay, while we bring it down, it will not cause any service unavailability. So the same process goes through. So the FM is the one that ensures that okay, like while we are doing the upgrade, everything keeps up and running.
Okay.
And it does several things. So one other thing that it does is the endpoint propagation, right? So when a service comes up and running, the user has no idea where the service is running, right? And how it's going to find the service. So this is where FM has the central view of all the replicas. It knows exactly which replica is running where, what is its endpoint, and then we have some protocol algorithm which disseminate all the endpoints to all the gateways and the clients, okay, in a in an efficient manner, so such that the load is not on a single node, right?
Sure.
And so then your question, right, the FMM, right? So the question is, okay, if FM seems like a very central core service, what if, where does FM run, right? How do we make that the FM reliable, right? So the way we model FM is no different than any other service. Okay, it's just like any other service. It has a partition, it has multiple replicas, primary, secondary, etc. It goes through the exact same reconfigurations, and that's how we make the FM reliable, right? Because if a primary goes down, we have other replicas, some other secondary becomes the primary. So the next question is, okay, so then who is doing the management of who's managing the replica set for the FM, right? And this is where we have this other component, FMM. So FM is managing the FM's replica set, right? And in fact, it only manages the FM replica set. It only manages a single partition, that's it. Okay, and this is where it's exactly the same code.
Sure.
It's the same algorithm that run. But then one may say, okay, who manages the FMM and then who manages that?
Yes,
right.
FM squared.
Who manages the FMM?
So no one manages the FMM because FMM is stateless, right? So,
I see.
So when it goes down, when the node that is running the FMM, if it crashes, if it goes down, all the state that FMM had is lost. Okay. And then we rely on the federation subsystem. I'm not sure if we have talked about federation subsystem in this series.
Not that much yet, but we might cover it in the future.
So federation subsystem gives us leader election. So we reliably elect another node as the leader to become the new FMM. And then the new FMM essentially does a consistent snapshot of the cluster. Okay, so
Sure.
to figure out exactly where everybody is, but it's only focused in the FM service. Okay, so it's not even looking at other services, right? So from that view, from all the reports that it gets from all the nodes, it combines those, stitches them together. We have some rules, algorithms, okay, different epochs, okay, which one is latest, which one is old, whose view is more recent. Based on that, it reconstructs the FM's replica set view. So it figures out exactly where the FM replicas are.
So this is what happens where if, for example, the FM just completely goes down. So
If the
in the case that the FM, it's more than just the primary, right? So suppose I had multiple primary nodes in my Service Fabric cluster. The FM was running on nodes 1 through, I guess, 3 or 1 through 5. And for whatever reason, CM and our other system services were in other parts of the same primary node set. And only the nodes that were running FM,
all of them are gone.
all of them are gone.
Right.
So then what happens?
So and this is also what happens when the cluster comes up for the very first time.
Sure.
Okay, so when the cluster comes up very first time, we don't know whether it's a brand new cluster or it's a cluster restart. Okay, so then FMM have no idea of where the FM is, so it doesn't know, it's stateless. So it again does this broadcast, ask everybody, okay, do you know if you have a FM replica? If you have a FM replica, it asks everybody, right? And if nobody replies back, then it concludes that, okay, this must have been a new cluster, brand new cluster, so it creates the FM service for the first time. Okay. Now your question, right? If the cluster restarts and all the nodes that were hosting the FM replica, if all of them are down, once again, FM is not going to hear from any node saying that, okay, it has a FM replica hosted on it, right? However, we do some more, when we collect information, we are looking for some more information. So if any node has any other replica hosted on it, okay, not just the FM, we are not interested in what it's hosting, but as long as there is the presence of any other replica, it implies that the FM must have existed on this cluster. So in that case, we just wait for the FM to come up.
Cool.
So which means that, okay, all the FM replicas are down. Okay, so we just wait in that case, okay, and until it comes up, or we take manual action to bring it up or do a full rebuild. So full rebuild is exactly the same rebuild that the FMM does, but this time the FM is doing to reconstruct the state of all the user and other system services. So,
cool. So let's talk a little bit more about the FM and feel free to grab the marker and stuff.
So if you look at the code, for example, we have the node cache, right? So it has a list of all the nodes that are up in the cluster, the nodes that are up, that are down, which UD they belong to. So for example, if I have to say, okay, up versus down, the UD, the FDUD is upgrade domain, fault domain,
Yep.
okay, properties, okay, and like several other things. Okay, for example, the port, the address, etc. The host name, which is important, right? So the name, and then of course the node ID. Okay. So it has a view of all this. So initially when the FM comes up, its node cache is empty. There is
No data.
no node, okay. But whenever a node comes up, the first thing it does is it joins the federation subsystem. Okay, but even after it joins the federation subsystem, it's still not in this view.
Right.
It yet has to join the reliability subsystem. Then it sends the node up message. Okay, so then if you look at it, this is the FM, and like these are all the nodes. Whenever a node comes up, it sends the node up information to the FM.
So the FM in this case is already running on a different set of machines.
It could be running anywhere. It could be one of these nodes.
Okay.
Okay, so for example, if it's a like one node cluster, everything is running on the same node. Okay, but conceptually it's a separate component. Okay. So, and the node up message contains all this information, right? And based on that, FM adds the node to its cache, right? And for staleness detection, etc., we also have the instance ID, which is always increasing. Okay, node ID, we assume that it is unique. Okay, like no two different nodes can have the same ID.
Sure.
And a hashing algorithm guarantees that. So this is how the node up comes in. Right? The view that we have over here is not necessarily the view that's in the cluster manifest. Okay, so when we set up a cluster, what we say, okay, we go to Azure and we say we need 5 nodes, right?
Yeah.
And it's not that, okay, we're going to start up with those 5 nodes. Okay, this is the actual running state of the cluster. Okay, so whatever nodes come up and respond, only they get entered in this list. So, and similarly, node down, when a node goes down, the node cannot send the node down.
Obviously, because the node is down. We actually had this bug in our eventing for a while.
Really?
Did you know that? The traces that we were exposing at some point, we were using the fabric node up and node down events. So you couldn't get a node down event because the node had gone down, so it couldn't inform you that it was down. So as of 6.2, we've actually fixed this to use the FM based event.
Right.
So when the event comes to FM for a node being up or down, that's when we publish that as a Service Fabric event, so that you guys can alert on it or have status or understand the status of each node. Basically.
Right.
Yeah.
So for node down, what happens is, and this is like more of a federation layer concept, right? So each of these nodes, they form a logical overlay network, which is the form of a ring, right? So it's a ring structure, it's overlay network. And in this ring structure, each node is monitoring its neighbors. So it establishes a mutual monitoring relationship, okay, and it's monitoring its neighborhood. And neighborhood is configurable, but I think our default is 3 nodes on each side. Okay, so each node is monitoring 3 other nodes on each side. And the way to do is, okay, constantly renew lease, etc. So if a node goes down, okay, it won't be able to renew its lease, and hence the neighbors will detect that the node is down. When the neighbors detect that the node is down, they send. So eventually, this information will propagate through the entire federation. But as soon as the neighbor finds out that the node is down, it sends a message to the FM. Okay, but the message is not explicitly saying that the node is down. Okay, it's a change notification message. Because, and the reason is, while the node was down, maybe it just restarted, and while this message is in flight, the node might have come up and it has already sent a node up message. So the change notification message says that okay, my neighborhood has changed. This is the new view of my neighborhood. That's all it says.
So for this particular node right now, this one, the neighborhood consists of these three on the right.
These three.
If this goes, does the neighborhood change to 1, 2, and then a third?
Another third.
Okay.
Okay. Or temporarily just these two until it adds the other one to its neighborhood.
Sure.
But all it says, okay, my neighborhood has changed. Okay. And these are the new set of nodes that are in my neighborhood. And there are other times where it authoritatively knows that a node is down and we have those nodes in the down list. But that's not really always there. Okay,
That's if there's a predictable reason for it going down.
So based on that, FM gets this. FM knows that okay, this node, for example, this node must have been in the neighborhood of this node. It's no longer there. So there is some algorithm, okay, like simple comparisons, okay, and it figures out that the node is down. So when the node is down, next what happens, right? So next, all the replicas that are hosted on that node, by definition, all of them are down. Okay, so then FM has the node cache view. So similarly, we have the service cache, which has list of all the services, service types, applications, and upgrades that are going on. Okay, so it contains all this.
This is also in the FM.
This is also in the FM. Okay. And so some of this information is also at the cluster manager, the service application, pretty much all of this. But the cluster manager's view is different than FM's view. Right? And then we have the, I don't know, I'm going to use this, the failover unit cache. Okay, so this is the important data structure. It has the list of all the partitions or failover units. So and which is a list of all the replicas.
What's the difference between a failover unit and a partition?
So no, there is no difference.
Okay.
So the way we have like today in the code, there is no difference. A partition, a consistency unit, and a failover unit are exactly the same. Conceptually, there is a difference, but the way we have modeled so far, there is exactly one-to-one mapping. Okay. Maybe in the future, okay, we have changes, but the way it is today, they are exactly the same.
And for the people that might not know, could you tell us a little bit more about what a partition is or what a failover unit is?
So failover unit and partition are the same thing. So a partition is, so for example, I have a service. And so for example, I have a service serving customers, right? So if I have maybe few hundred or few thousand customers, okay, I have one single machine server, okay, which is serving all the requests. Okay, it's good enough. It can request all the requests. However, if the load increases, right, the number of customers increase, right, I have an app, right, it's very popular, everybody is installing it.
Yeah.
Okay, I have millions of customers, right, so that single machine can no longer serve all the requests, right? Or the data associated with the customers is too much to fit on a single machine. So in that case, what we do is all the state that we have, we partition it, okay, or we chunk it, okay, and each chunk is called a partition. Okay, and it is served by a different machine. Okay. And the way we partition is like we can have several partitioning schemes, right? So, for example, in the case of the customer, we can say that okay, all the customers whose name start with letter A, that's one partition. Letter B is another partition. Another scheme could be that okay, all the customers in New York, they are like partition 1, in California, partition 2, etc. It could be any partitioning scheme. So the idea is just divide the entire state into smaller chunks and have them process each chunk separately.
So that sounds like sharding.
It is exactly the same thing. Yeah. Okay. So that's a partition. Failover unit is that if there is a failure, what is the unit of state that fails over to another node? Okay. So in our case, it's exactly the same, right? Because one partition is running on one machine. So if that machine goes down, the entire partition needs to be failed over. So it's exactly the same thing. Okay.
Yeah.
And similarly, there is this other concept, consistency unit, that we also use elsewhere in the code, which is that, okay, even though they fail over together, but are they consistent together or not? Okay, maybe if half of them failed over, the other half is still consistent. So, but in the way we have implemented, like today, they are exactly the same. So we have we have this state, and this is where we have a lot of this state. Okay, so for example, we know that for each replica, whether it's a primary, whether it's a secondary, whether it's up, whether it's down, whether it's ready, not ready, what's its endpoint, version for upgrades, etc. There's a whole bunch of information associated with each replica, and similarly for each partition. So FM has a state machine model. So in the background, it has a state machine that's constantly monitoring the state. So essentially, like, this is the most important state, because this is event driven, right? Okay, like something happened. Even this is like service create and delete. Even though this is event driven, but this is, for example, if a node goes down, then the state machine, we only mark the node as down on that event. Then the state machine in the background, it realizes that, oh, the node is down. So then it marks all the replicas on the node as down.
Right.
Okay, and so then when it detects that a node is down, the replica is down, what it needs to do? So what the state machine is doing is it's constantly trying to get a partition to its target state. Okay, regardless of where it is. Okay, so that would we call a state machine based approach, right? So for example, so let me take, before I cover this, let me take another example, right? So when we create a service, okay, so let's say I create a service foo with one partition and target replica count of 3. Okay, so the request comes to FM. Over here, FM creates a service object, an application object. Over here, it creates a partition, okay, failover unit object.
Right.
Okay.
With 3 replicas.
No, so with target equal to 3. Okay, with no replicas. That's it. And the call returns. Next, the state machine runs. And the state machine notices that, oh, the target is 3, but I don't have 3 replicas. So this means that I need to take some action to bring the partition to the target state. So at that point, it will
Start building.
It will talk to PLB. So this is the other component that FM closely works with. In fact, PLB resides with the FM.
When you say resides with, you mean they're in the same process, or?
They're in this, well, FM is in the fabric.exe process,
Right.
It's not in separate. But it's on the same node as the FM. So when we start FM is the one that says, okay, new PLB. So it has this component.
You're the father of PLV.
Father of PLB. PLB is not
The
a
creator.
PLB is not a separate service. Okay.
Okay.
So the same is with the health manager, right? Health manager resides with the cluster manager.
Yeah,
it's not a separate.
So PLB is a bunch of algorithms that are
PLBs
used.
are load balancing algorithms.
Exactly.
Yeah.
Placement and load
So
balancing.
we'll talk to Yang about that in some
Right on.
Yeah.
So PLB's view is pretty much the same view, but not as detailed. Okay, so it doesn't need to know everything. It only needs to know enough things so that it can load balance and do placement. So then FM says, PLB says, okay, hey, I have this partition, but I need 3 replicas. I don't have the 3
Sure.
replicas, right? PLB runs its algorithms, okay, it knows, okay, exactly where we have more capacity in the cluster, okay, or which nodes are less overloaded. And based on that, it says, okay, here are the 3 replicas, create on node, replica 1 on node 1, replica 2 on node 3, and replica 3 on node 6. Okay, for
Sure.
example, right? So it says, okay, this is where you go and create the placement. So then what we do is we add these 3 replicas. Okay, so we have added these 3 replicas. Then the state machine runs again. Okay, and then it notices that, okay, well, even though I have these 3 replicas, they are not ready and up yet. Okay, so I need to, because at this point, it's just the objects created, right? There is nothing actually running.
Right. Yep.
Right? So then it sends, so this is where FM interacts with RA, and RA is running on each node.
Yeah.
So for node 1, for placing replica 1 on node 1, FM would send a message to the array on node 1 and ask it to create this replica.
Yep.
Okay, and same thing for the other replicas. So in that message, FM would provide enough information for RA to be able to create those replicas. Okay, so now the call goes to RA, and RA says that, okay, well, this is somewhat of RA, and you can tell me if AP has already covered this or not, right? So RA would say that, okay, I have this replica that I need to create, and this is the associated code package, but I don't have the code package. So it asks hosting to, okay, start this code package, right? And RA is working with hosting, and hosting says I don't have it. So then hosting goes to the.
It sounds like the way government works. Just kidding.
Except this happens in seconds.
Understood.
so then it goes to our image.
Image store.
Image store, right?
Yeah.
And image store says, okay, I need this package, okay, this version exactly, okay, like exactly what I need. So it downloads the package. Okay, and the package is just the executables and the associated configuration files, right? So then it starts running the process. Okay, so when array starts running the process, then it sends a reply back to FM saying that, okay, now this replica is running. Now FM says that, okay, now it's ready. Okay, and similarly like other replicas. Okay. So now, once all the replicas have been created, and for stateful services, then of course it has to do this reconfiguration, right? Like one of them is a primary and others are secondary. Okay, so this is how it works. Right? So now coming back to the failure case, when a node is down, FM is going to detect that there is a failure. So the next time the state machine runs, it will say that, okay, yeah, this one is down. Okay. And then it will notice that, okay, the target is 3, but I have only 2 that are up. And then, of course, we have some configurations that, okay, whether to wait for this one to come up or create a new one. So based on the policies, right? So if we decide to create a new one, then FM will again ask PLB that, okay, I need one more. And PLB will say, okay, here, go and create on this node. And FM will create on this node. And then it will say that, okay, well, even though it's created, it's still not part of the configuration. It's not a primary or secondary replica. So then FM will trigger a reconfiguration. Okay, so FM will ask RA to do this reconfiguration. Okay, if a primary goes down, same thing, right? It notices that, okay, even though I have a partition, it doesn't have a primary. So FM is the one that comes up with the final plan for a configuration set. Okay, so this is the current configuration. Something happened. This is the new configuration. It tells this plan to RA and go and implement this. And then RA takes on the responsibility of communicating with all the other replicas in this set to get to that configuration. And then it sends the reply back. And the reason we have done it like this is to delegate as much work to the nodes so that FM doesn't become the bottleneck.
Makes perfect sense.
Interesting. So FM, to what extent does FM care about primaries versus secondary replicas? Or that just, yeah.
No.
So that's part of the cache that we have.
That's part of, okay. So this is just the failover aspect, right? But then, as I said earlier, right, FM is doing more than that, right? So there are other times where PLB initiates reconfigurations, right? And that happens if the load distribution changes. So while everything is running, right, we can have replicas report load, right, how overloaded they are. So they are reporting load to FM. So FM is also, so in addition to this, we also have a load cache, which has a record of the load of all these running replicas.
Is that load in terms of incoming requests, or is that load in terms of how much resource utilization it's taking up on the node?
The load is defined based on abstract metrics.
Okay.
So we say it's up to the customer how they define it. So we say, okay, metric A, load, this is the load.
So it's a fully logical boundary.
Metric B, and it's up to the customer. Okay, A means incoming request, B means disk capacity, C means CPU, etc.
Oh, so really, so it could be a combination of logical and physical metrics.
Yeah. And of course, there are some things which are global to that node, for example, CPU.
Yeah.
But there are other things like how many ports opened, right? That's unique to that application. So it's up to the application however they want to define the metrics and what they report on these metrics. Okay. So when the load comes to FM, then FM updates the PLB that, okay, like this is the new load, right?
Right.
All the cluster has reported, right? Based on that, PLB says that, okay, yeah, maybe this node is getting too much overloaded. It has too many primary replicas. Let me move them around. Then PLB comes up with the plan. Okay, so it runs its algorithm and it says, okay, move this replica over here, move this over here. Okay, swap the primary, secondary roles of these two replicas,
Right.
etc. And then FM then again comes up with it. PLB just says, okay, this is what need to done. Okay, and then FM makes the actual changes of, okay, primary, secondary, etc. And then once again asks RA, go and implement these new configurations.
So the FM is the one that really keeps track of the configuration, even though it's a reconfiguration agent that executes on the required configuration.
Yeah.
For a set of.
So while a reconfiguration is going on, FM is the one that has come up with the final plan. Okay, and RA is trying to get to that final plan.
Sure.
Okay.
So one of the hard problems that exists in distributed computing today is detection of failures. So when you give this example of these 5 nodes with the middle one going down, what are the things that we do to best identify whether or not that particular node has actually gone down, and then predictably do whatever has to happen with the
So I think this is more of a federation layer concept.
Okay.
So of course we have leasing, right?
Yeah.
So the lease is we have mutual monitoring relationship. So each node gets a lease from its neighbors. So I think the default, I forgot the term, I think 30 seconds.
30 seconds is
right. So it has to renew its lease within that much time. If it doesn't, then it's in doubt. Okay, we don't know whether it's up or down. We are always in doubt. We can never say 100% whether a node is down or not.
Schrodinger's node.
Right? Because what if this node stays up but gets disconnected from the cluster? It's a network partitioning. So in reality, the node is not really down. It's still up, right? So we don't know. And similarly, like other neighbors would also detect the same thing. And so in the federation subsystem, we also have this concept of an arbitrator. So whenever the nodes are in doubt, they go to the arbitrator. An arbitrator is the set of seed nodes. And if a majority of them, then they decide, okay, but who is right, who is wrong, right? Because this guy might be saying, oh, node 5 is down. Another node might be saying node 5 is up. So whether node 5 is really up or really down, okay, it's really hard to say that. So arbitrator is the one that decides that. And we have some rules and algorithms over there. And whatever the arbitrator decides, that's
final.
That's the final thing,
Sure.
right? If the node is actually up, but the arbitrator has decided that it's down, it goes down. Okay, it has to commit suicide, right? Because there is no way it can join the cluster again.
Sure.
It has to restart so that it gets a higher instance ID, a new incarnation, and only then it can join the cluster. And since you brought that up, right? So what happens if the network gets partitioned, right, into 2 chunks, right? See, we don't want to have a split brain situation where, like, on one half we detect some of the replicas are down and we reconfigure them. On the other half we detect the same thing and we reconfigure them. And then both halves start making progress and the consistency of the data is diverged, right, in 2 separate streams. You don't want that to happen, right? So to prevent that, we have the seed nodes or the voters. So we always require a cluster to have a majority of the seed nodes. So whenever network partitioning happens, only one partition can have majority of the seed nodes, okay, not multiple partition. And only that partition survives, others go down. If there is like 3-way partition, it may happen that, okay, none of them have majority, then everybody goes down. So one basic principle we try to follow across reliability failover is we give preference to consistency over availability. So if something is not safe, okay, from a consistency point of view, from a data integrity point of view, we may halt progress by default. Okay, of course we have configs and tweaks to get all sort of behavior, rather than going like eventually consistent and trying to make progress in hope that everything would be okay. We don't do that.
Sure.
Okay, so
That's, as AP said, consistency is.
we should strongly consistent.
It's a core tenet of what a server is.
Absolutely.
Right.
And you have to guarantee that.
So it looks like the FM is mostly just a set of a bunch of caches that have a lot of info about the entire state of a cluster.
So I think the main logic is in the state machine, right? Because this information is also available elsewhere in the cluster as well.
Okay.
But how do we react on based on the state?
Cool.
Okay, so for example, if something is down, so it's not that we can just randomly pick someone as the new primary, right? So we have all these rules. Okay, AP must have covered that based on the epochs.
Yeah.
Yes.
The
Yeah,
view
we done
numbers,
one.
right?
Yeah.
What is the view, the read-write quorums, etc.
Yeah.
Right? So based on that, we decide, okay, like how things should proceed. Okay, and what happens if there is a quorum loss? Okay, and majority of the replicas go down. Okay, we just halt progress for that partition. We cannot elect a new primary. We just wait, right? And in case a primary goes down, we have multiple candidates. Which one to pick as the new primary? So I think all that complex logic that goes around the state, that's the core functionality of the app.
So that last thing you mentioned, could we go into a little bit of detail with that, which is just the simple scenario where the primary replica goes down?
Mm-hmm.
How do we decide to move to the secondary, or which secondary do we decide to choose as in terms of the state manager?
So typically whenever we have a failure, we consult PLB. Okay, like what is the best candidate? However, and PLB can take its own sweet time deciding, right?
Right.
However, primary going down is resulting in immediate unavailability of the service. So we don't want to wait unnecessarily. So in that case, still FM, like there is one small call into PLB. It's not doing any load balancing algorithm at that point. So to check some quick constraint, right? Because there are also constraints. So I didn't mention. So we also have the placement constraints and all those things, right?
Yeah.
So then it gets back like few candidates, right, from the PLB, and among those it just picks one randomly. So most of the time, everything is like healthy, everything is fine. The primary goes down among the set of the secondary replicas is just random, okay, or like the first one in the list. So we pick that as the new primary. Then we go and tell RA that, okay, like make this the reconfiguration, and we tell exactly what the epochs are, etc. Right. So in the reconfiguration, the first phase of reconfiguration, the get LSN.
Yeah.
So the primary elect, it asks everyone else, okay, what is your progress? Okay, because some replicas might be ahead of the primary elect.
This is sort of what we talked about with Sumak.
Right on.
Right?
Yeah.
It's all coming together. It's no, it's great.
So then we may figure out that, okay, the secondary that we elected to be the new primary is not the most advanced replica. So some other replica is the most advanced. So then what happens is that a message goes back to FM with all the progress details of the replicas. So then FM comes to know of the progress, and based on that, FM picks the replica with the highest progress. And then it starts another reconfiguration. Because whenever it changes, it's another reconfiguration. So let's say we started going from E1 to E2. So we find out that, okay, the primary in E2 is not the most caught up guy. So a message will go back, then FM will start another from E1 to E3.
Right. Correct.
Okay.
Yeah,
so
we
this
saw
one
this
stays
with
at
AP.
E1 until the reconfiguration complete.
Yeah.
So like E3, E4, E5, because while the reconfiguration is going on, failures may still happen. So anytime a failure happens, the epoch changes, and once the reconfiguration is complete,
Then only do we switch. Until then, we stay at E1.
and this is what we use a lot in the when we reverse engineer this whole thing in the rebuild. So we rely on these properties.
Interesting. So FM is really like the core orchestrator, basically, in Service Fabric.
And then if I have to go into upgrades, for example,
that's true.
right? So I mentioned fabric upgrade, application upgrade, and also the patching of the node or the OS upgrade, etc. Right? So it's pretty much the same algorithms that run, but if I just pick like application upgrade as an example. So the upgrade request comes to FM, says that, okay, like this is the new version, okay, like we have upgrade specification. In each application, we can have multiple service types, multiple code packages. It may not be that we are upgrading all of them at the same time. Okay, we may be upgrading only one code package. So the first thing FM does is identify exactly what in the application is getting impacted from that upgrade.
Is this based on versioning or is this based on an actual check of what's in the code package?
No, we don't inspect the code,
Okay.
the code package, right?
So we expect that users
So
actually
in that specification, we have a list of types
Right.
that are getting upgraded and the corresponding version.
Yeah,
Okay.
but if somebody suppose somebody increments a version just for fun without changing the code package,
Yeah.
we assume that that's actually being upgraded, right?
Yes. But if you're just changing the version and like no type defined, okay, like nothing real gonna happen. So then we identify exactly what partitions need to be upgraded, right? So impact. So then we start doing this UD walk, right? So like we start from UD1. And the first thing we do is, in order to minimize the downtime, we swap out all the primaries from that UD. So all the primary replicas get swapped out elsewhere in the cluster. Okay, and then it's only the secondary replicas or the stateless instances. And then we do what we call the safety checks. The safety checks say that if I were to bring this node down as part of the upgrade, unless it's a notification only upgrade where the process doesn't go down, typically the process goes down. So then the question is, if this replica is to go down, is it going to cause any availability issues? If the answer is yes, then we just pause. Okay, so then this is where we see all those upgrade stuck incidents, right?
Right.
So then we say, okay, no, it's not safe, we're not going to proceed. And if it is safe, only then we proceed. However, while we're doing these safety checks, we are also, in addition to just the quorum-based safety checks, we also do some non-quorum-based safety checks, which are the nice-to-have safety checks. So, for example, if a partition is going through a reconfiguration, we wait for the reconfiguration to complete. And typically, a reconfiguration lasts only a few milliseconds, so that's not really an issue. However, if there is something wrong and the reconfiguration is stuck, okay, then we pause, okay, we don't want to make things worse. Because it may so have happened that in the new code package there is a bug and the reconfiguration is not completing. Similarly, if a primary replica, so the primary replica is the one that builds new replicas. So whenever, for stateful services, whenever we create a new replica, it comes up as empty. Then it gets all the data from the primary replica. And for some of the services, it can be like terabytes of data. So while the primary is seeding these new replicas, okay, we pause, okay, we don't upgrade those replicas. We wait for them to complete their build. So it does all these safety checks, and then it sends a message to RA and saying that, okay, go and upgrade this set of code packages. And RA does pretty much the same thing. Okay, it closes all the replicas, and after that it tells hosting, okay, now start these replicas in this new version. And RA says, okay, hosting says, I don't have this version. It goes to image store, download the new binaries.
That's awesome.
Runs those new replicas in the new version, and then replies back to the FM, and FM is keeping track, okay, like whether everybody has upgraded or not upgraded. And then FM says, okay, this UD is done. Once all the nodes in the UD are done. And then, of course, it's the health policies, right? So whether it's a monitored upgrade or unmonitored upgrade and all those things. And then it moves on to the next UD. Okay, and so on and so forth. Okay, so this is the safety check part of the upgrade. And the same thing happens for Fabric upgrade. The difference is in Fabric upgrade, everything is impacted.
Sure.
Okay, so not just one application, but all application, all replicas, system services, everything is impacted. So, but otherwise it's the same thing.
But that's interesting though, because it's the actual underlying system services that are changing. So FM is going to be upgraded to 6.3.
Yeah.
Correct.
Right? And then FMM is going to be upgraded as well, because maybe they
Correct.
share 95% of the code.
Correct.
Maybe there's actually different changes in FMM that had to get fixed.
Correct. So that's why that's why the backward compatibility comes in. So any change that we make, we want to make sure that it's backward compatible, both on what goes on the wire as well as what gets stored on the disk. Okay, so for example, FM replicas on like primary, secondary, like on these 4 UDs, we may have upgraded these 2 nodes. Okay, and the primary could be running on the new code or the old code or the new code, okay? And it may move around while the upgrade is in progress. So the only guarantees are that, okay, once the upgrade is complete, then everybody is running the new version. So while the upgrade is in progress, both the old and new protocols should be able to talk to each other.
So you actually simultaneously have both versions running until.
Correct.
Interesting.
Correct. And there are rare cases, like it's not recommended, but every now and then we come up with some protocol change that does not work with this dual mode thing. So in that case, what we do is what we call the two-phase upgrade. So we have all the new code, but it's disabled by a configuration. So we do the first upgrade so that everybody has the new bits. Okay, and then we do another upgrade which enables that new functionality. So that's a way to get around backward compatibility. But still, okay, like depending on what it is, it may or may not work.
Sure.
And does the FM get updated first, or does the FMM get updated first?
Doesn't matter, right? Like depending on like the UD one gets upgraded first.
Whatever is the UD one. Cool. And I mean, you've worked on the FM for years. What has been like some of the main challenges that have stood out to you, or making this thing as optimal as possible?
So I think, of course, performance optimization is always there. Okay, and I think it's not gonna end. There is no point where we say that okay, it's fully optimized. Okay, there is no room for optimization.
Yes, because you can always optimize more.
Yeah, we can always optimize more, right? So for example, okay, when we are trying to get to that million replica
demo that we did with Marcus.
Demo, right? So FM had to like have million replicas over here, right? And then I don't know how many services we had, everything. And so then what happens is, in such large systems, right, if a failure happens, we don't want to get to a point where like there is so much load in the cluster that we cannot recover from it. So let's say if everybody started sending FM messages, in the worst case, that may become a DOS attack, right? Because then FM will be overwhelmed with all the incoming requests, everything. So it won't be able to do any work. So we had to do a lot of work. For example, the job queues. There is a time where we say, okay, we stop accepting new work. We try to complete existing work. We change so instead of processing requests in the FIFO order, first come, first serve, we process them in the reverse order, last in, first serve. Because the last message has the most up-to-date information. The first message that's sitting in the queue for, I don't know, several minutes, it might be already stale. So we don't want to work on that. So these are all those performance types, right? So, and I think that's how we were also threading, okay, we don't want to block a thread, etc. All these standard things. In terms of actual algorithms, I think the main challenge is in competing requirements from customers. So everybody is coming from a different angle, and everyone is looking for a slightly different behavior. So coming up with a policy that makes everyone happy is the most challenging part. So let me give you an example, right? So for example, when it's time to decommission a node or repair a node, so let's say hard disk was bad, right? Or like we suspect the hard is going bad or there's a hardware problem. So Azure does this reimage thing, right? I'm going to reimage that machine. So what we do is eventually the request comes to FM via MR. And so then we said, okay, we want to be nice to the user, to the actual customer who are running their application. So we will gracefully move everything out of that node. Okay, we'll drain everything from that node. So which means that at no point we will even have a chance of quorum loss, unless there are other external failures happening. So we'll first create replacement replicas, and then we'll reconfigure them so that, okay, there is no point where we have less than quorum number of replicas. Okay, works fine, okay. And then somebody says, I don't have room in my cluster to create those replacement replicas. Yet I also want to be safe. Okay, so how do we do that? Right. So this is one example, right?
So how do you do it? What do we do?
We cannot make it safe, right? Well, it will still be safe. We'll still have quorum number of replicas, but not necessarily target number of replicas. So there will be a point of time while the reimage is happening, for example, right, will be less than target, unless we have capacity elsewhere in the cluster.
What would be your one piece of advice to somebody who wants to contribute some code to Service Fabric now that it's open source?
One piece of advice. So I think I would say that, okay, only work in the area where you are passionate about. It's not going to be easy. And yeah, go where your passion is. And at the end, like, produce quality code, right? Because at the end, code speaks.
Cool.
That's the output.